this equation, but in streamline coordinate. Compare the term and draw a similarity between the two, and hopefully all this will reinforce what we're talking about. Right? At the time, we also neglect gravity, and we assume the problem is steady. And from that, we come up with the Euler equation. Sorry, we come up with now the Bernoulli equation. Questions? Okay, now let me jumpstart. So this is just a review so we can put things in perspective. This is what we did in the lecture prior to Thanksgiving break. Like I said before, is on the basis of forming that differential element again, dx dy. I'm not going to draw the z direction, and except this time theta become momentum as opposed to continuity of rho u. Theta become now rho u squared. And then we have this equation shown just prior to spring break, prior to Thanksgiving break. Any question on that? Now, I won't hold you responsible for that because this is a little bit more in-depth, but you should be capable and comfortable enough to actually derive that based on this technique. What shown below are fancy footwork, and it's mainly using vector notation of gradient and dot product. So the equation of a set of three, x, y, z, can be represented by a very elegant one equation form using vector notation. Gradient, total acceleration, all those should not be a surprise to you. Questions? Now the main takeaway I want you to be able to digest and relate to is with all this fancy derivation, as I alluded to right at the end of lecture, spring break, or rather actually before the last lecture of Thanksgiving break, this is nothing but different, just as F equal to MA, with one caveat. This is not force on left side, right side. What is the denominator? Not area, but close. Tell me what is this term? Velocity? It's an acceleration. What acceleration again? You're missing one word before the acceleration. Total. So I have total acceleration, which is this guy. What's density? What divided by what? So what's missing in the denominator? 1 on both sides. So all this fancy footwork is just go back to Newton second. That I will hold you responsible for. That you can see, and that you can relate. Questions? Questions? So now with that, I'm going to extrapolate to my equation of motion for the Holy Grail, which is everything inclusive, including viscous count. All of a sudden, the implicit vector notation consists of this term in here. This will be body force per unit volume, pressure force per unit volume, multiplied by the acceleration times a mass per unit volume for implicit equation, which I repeat here. Gravity, pressure force, acceleration times mass per unit volume. The missing question mark are all these terms here due to viscosity. And they have a second derivative with respect to the coordinate. And the reason they come about just the big picture, very high level. Nutshell type approach is, can someone remind me what shear is being calculated? What is that equal to? It's not something I think you're going to remember, but I hope at least some of you do, from how we define viscosity at the very beginning of the semester, how is shear calculated. Anyone? No? Okay. Viscosity times du dy. Remember that? Remember that? From this problem of a plate moving along with V, where at the time we assume the velocity is uniform and linear. And from this we define the viscosity. Same thing here. Same thing here. So if I have that shear on one side, on the top surface, now I move a distance of dx on the other side, you will expect to have term where d theta is now moved by the distance dy. You have something like the viscosity, which is times the velocity gradient, differentiated with respect to y again, resulting in a second derivative term such as this, right? So that's the origin of this new added term that's driven by viscosity, without diving into the deep end, just to give you a sense as to how this come about. The exact derivation is in the text, and you are certainly more than welcome to read it. Okay? So I would like to leave you at that, yes?
Could you explain again why you differentiate?
Because remember, the building block of this approach is where I have a differential box of dx dy and a quantity theta, and then when I move, you have theta plus d theta dx, in this case multiplied by del x, right? That's the foundation of how we get the Euler streamline equation. So I'm applying the same technique over and over again. First continuity, and then the Euler's equation of motion. And now finally, I want to account for the viscous effect. And I'm applying the same building block. And now the theta, in this case, is my shear stress. And then when I go through that, I will find out a term that is a second derivative. Are you with me? Questions? Okay, that part of it I won't necessarily have you be responsible for deriving. The fancy footwork that follow will have an implication in your future classes in control, and also in things like migration, which happen to come up with a Laplacian operator. And it's just nothing but taking an approach to simplify this rather lengthy equation and be able to present that in a vector notation at the end. This is just algebra. You can read that yourself. And what that added term due to viscosity now can appear in here. And as to how all this vector notation coming about is all but not algebra. The Laplace operator, which you will see again in higher level classes, is just by definition this operation. All right? So at least be alert of it. You will come back and see it again in your senior year. So that's it. That's the equation of viscous flow. Any question? Okay, so I would then take advantage of all this and use it for the inclined plane problem. Everyone's good? Okay, very good. So a couple of comments related to the equation before I start talking about the inclined plane problem, which is, so NS stands for Navier-Stokes equation, named after the two gentlemen, one the British, the other one is Frenchman. It's a second order because you have term like parcel of u, parcel of y, second derivative. Nonlinear because they are all coupled because of the velocity term and the viscous term in such a way that there's no easy closed form solution to solve this Navier-Stokes equation. So we solved that many PhD given just to see how you can solve this half a century ago by slide rule, you know what that is, and mathematical table like error function. So that was the war story I told you about Professor Prentos and his team of students. We're going to come back to that. Even nowadays with supercomputer, still takes weeks to solve a differential equation of this nature for a turbine engine that's in the hallway, for one component, not just the fan, not the whole engine, right? So it's a very challenging equation. From a big picture perspective, you know, it's just still the same physics. We have four unknown, what are they? Three velocity component and a pressure. And it turns out we have three equations, x, y, z. I have four unknown. I need one more to close the loop. What do you think that equation is? Continuity. Sweet old continuity. PhD, you still go back to the basic. You need continuity. Just like you would